Hi, everyone. Welcome and thank you for joining us for today's talk. We are very pleased to introduce Alexander Chiasson, who will be talking about his project on variation in the morphology of permafrost peatlands across the transition from continuous to discontinuous permafrost in central Mackenzie Valley. So I'm going to just briefly introduce Alex and then we can listen to his presentation. So Alex started his PhD at University of Alberta in September 2020 under the supervision of Dr. Dwayne Frost. Prior to that, Alexander did master at University of Laval with Dr. Michel Allard on the distribution and development of thermal contraction crack polygons in Nunavik using a semi-remote sensing approach. His initial PhD project aimed to develop a geological model of ground ice along the proposed central Mackenzie right-of-way, but his project got affected by pandemic. Now, Alex is interested in dynamic and variability of peatland morphology of the central Mackenzie Valley, with a particular interest in dendritic peat plateaus, which he will be talking about today. Alex is currently between two internships with Dr. Steve Cockell and Ashley Rudy at the Northwest Territories Geological Survey as a GIS specialist, working on the thermal karst mapping collective and other GIS projects.
Thank you for everybody who is attending my presentation today. I'm very excited to talk about my research and what I've done so far in the central Mackenzie Valley, located in the Northwest Territory. So today I will mostly talk about peatland morphology variability, but also talk about change detection within the Nordic Peat Plateau. Those two topics are the first two chapters of my PhD, and I will conclude with an overview of my chapter number 3 and 4. Those are still an early stage of development, so I don't have a lot of data to share, but it would be nice to have just feedback. And if anybody have comments, it would be appreciated. So I would like to thank and show acknowledgement to the Satu Dene where my project takes part. And like Zakia she did a good introduction about me. So I did a master with Michel. And after that, I worked for him as an associate researcher on permafrost community mapping. And when Michel retired, I'm with Dwayne Fraser at ULA to start a PhD. And now I'm working with Dr. Steve Cockell and Ashley Rudy at the NTGS as an intern, mostly work on GIS project. And so this is my supervisory team, Dwayne Fraser, Ashley Rudy, Steve Cockell, Sharon Smith, also working with Urin at the Geomatic Center at the in Yellowknife. Neil West, it's a new employee at the NTGS. He helped me with the coding. And Kathleen Lavage England, she is a biology researcher here at UAV, and she's helping me with the macro analysis. So I'm going to just present some concept that I'm going to talk about today. I know that most people here has permafrost background, but maybe there are some that didn't really know permafrost or even been on scale and see permafrost. So I'm going to mention fans that are minerotrophic precipitation. Usually those are alimented by precipitations and groundwater. There's also bogs. Those are more close environment only alimented by precipitation. There's peat plateau where we have permafrost there. Collapse core and collapse border following permafrost thaw, and channelized fan or fan occurring in a topographic well-defined channel. And those channelized fan form dendritic pattern I'm going to explain today. So now let's start on the variability of dendritic peat plateau and peatland. So the effect on permafrost peatland morphology and permafrost peatland formation, morphology, and evolution are crucial in predicting how peatlands will respond to climate change. With almost 20% of Canada peatland in the central Mackenzie Valley, this is a very good location for studying the variation in the morphology of permafrost peatland across the transition zone from continuous to discontinuous permafrost. While previous research has provided a foundation for understanding the peatland morphology, there has been limited research on the variability of the morphology of permafrost peat plateau degradation. So in this presentation, I will try to present important insight into how the geomorphology and drainage pattern of peatland and discontinuous and continuous permafrost zone change and is affected by climate change, with a particular focus on dendritically trained peat plateaus. So I'm going to use the term dendritic peat plateau. It's more simple. Is I can see here in the figure those two red stars are two sides. I went and I look at the morphology of dendritic peat plateau for a local scale. So I'm going to mention the four globe site, this one, and the mountain one. It's the one right there. So while many researchers have developed models to predict that trajectory, it is important to recognize that permafrost had its unique characteristic shaped by location, past history, and local environment for condition. For example, this conceptual framework showing a temporal and constant a northern constant right there. So this framework showed that the peatland will change and evolve from the north to south. However, the framework neglects the permafrost component of the discontinuous permafrost zone, which include ice wedge polygon networks, buried ice, relic ice that will shape the northern landscape. Including this permafrost component, the northern region, it is very unlikely that in the landscape will evolve as the same way as in the south, because permafrost is way more different in the north than in the south. So we need to start thinking about the component that affect the landscape and how they're going to evolve. And in this case, a person used something in the south and say, okay, that's and just reconstruct it instead of and forget to take into consideration what we have in or like ice wedge polygon. And the goal of this talk is to talk about factor that will influence the morphology of peatlands and how they're going to evolve with time. And so, for example, the historical context of the peatland formation, including the timing and duration of glaciation, can also play a crucial role in shaping the current characteristic, which will influence the pattern type, hydrological regime, and peat accumulation rate of peatland. So therefore, understanding the variability of peatland require a detailed examination of their local context and their unique historical and environmental factor that shape them over time. So the talk is going to be about local setting and factor that influence dendritic peat plateaus and peatland morphology in the central Mackenzie Valley. So this is another example here of different peatland uh, across the NWT. So we have lake for ice polygon and apps core in basin. This is a dendritic pattern here close to Fort Simpson. And we have here, and so when previous research has recognized the significant variation in peatland morphology across the NWT, the intra-variability within peatland landform, which affect differently the biophysical, hydrological, and permafrost regime of each peatland landform, have never been documented. So to address this knowledge gap, our study aims to investigate the morphology and pattern of dendritic peat plateau along a latitudinal gradient in the central Mackenzie Valley. So by doing so, we hope to gain insight into how factors such as climate, terrain, and permafrost condition contribute to the evolution and degradation of this very sensitive landform. The objective of this project is to describe dendritic peat plateau morphology and composition, but also to determine their distribution across the central Mackenzie Valley. We aim also to analyze the variation in morphology pattern and investigate potential controls on this variability. So this is a picture of how it looks like a dendritic peat plateaus. But first, what are dendritically drained peat plateaus? So a dendritic peat plateau is a type of peatland that exhibits a branching network of channelized fens, which dissect the organic deposits and connect with other similarly oriented channels. They are characterized by irregular branching tributaries. And if we look at this picture, this one is a very textbook picture of a dendritic peat plateau network, and they look like a trees. So this is why we call them dendritic. This is from dendrite, that is from the Old Latin. And this landform is very common throughout the central Mackenzie Valley, but the morphology can vary significantly. So we aim to understand this variation within peatlands. So we went on the field into 2021 and 2022, and we select three sites that are very different characteristics. and we drill a borehole and carry out ERT survey. So ERT survey, it's a very good tool for to use in discontinuous permafrost, because permafrost is gonna exhibit a higher resistivity, so a higher value when you look at the result, and whereas unfrozen ground has low resistivity. So permafrost or bedrock have higher value, and where we have unfrozen ground, it's lower value. And we also use the basal peat for C14 to know the age of those landform. And I want to bring you your attention right there that this is a stratigraphy of the dendritic peat plateau, and we have almost 2 meters of thick. And after that, we have a nice rich dynamic with aggregated and segregated ground ice, and it's very important for the discussion section. So just keep in mind that they are formed of 2 meters of peat overlying by ice-rich dynamic deposit. And this is a nice picture of a core we drill, and this ice lens here is almost 20 centimeter of just per ice, and it's just below the peat at 2.7 meters. And so to also determine the extent of thermocourse degradation within peat plateaus, we use 4 sets of aerial photographs, 2 from the National Air Photo Library, 1 from the 40s, the other one from the 70s. But also we ordered an aerial satellite imagery from Maxor at that date from 2011, and we have an S-spot imagery 1.5 meter resolution for 3 sites. So I digital all those sites. Took me a while, but I finished. Now I'm writing the paper on the change section. And so we classified the dendritic peat plateau into 5 classes. So we have the fen, the permafrost free bogs, the pond, the peat plateau, and the forested area within the peat plateaus. So we use a very precise scale at 1 to 500 to be able to identify smaller features such as recent bogs and coulees, to be sure that to capture the formation of new bogs between 2 sets of aerial photographs. And to know the extent of the dendritic peat plateau across the central Mackenzie Valley, we implemented an approach built over the thermocourse mapping collective by assessing the presence or not of dendritic peat plateau across the valley. So what we did is we use a grid cell mapping approach, and we divided the territory into different cells, and we had over, I would say, more than 200,000 grid cells, and we just look one by one, say, okay, presence or not of dendritic peat plateau, yes or no. And from that, after that, we create this multivariate analysis sheet with characteristic of dendritic peat plateaus. So when we have only our cell including dendritic peat plateau, what we did is we use a subset tool that we only keep 35% of our dendritic peat plateau cells within ecoregion, and we characterize the grid cell. So we have, for example, the drainage orientation. So if they're drain north, east, south, and west, and the degradation, the presence of string bugs on peat plateau or channelized fens, the type geography. So if the dendritic peat plateau is affected by pond, collapsed coral lakes, and basins, and the most important is the branching pattern. So we want to know the intra-variability within the different type of dendritic peat plateau. So we look at different location, different form, and we finish with 4 kind of drainage pattern that are all dendritic, but a bit different. So we have the parallel one. This one is linear. The classic one is the dendritic one, the textbook one that I showed in the video. We have the complex, that it's a multi-basinal complex dendritic pattern, and rectangular, that this one is a dendritic pattern, but with more the channels and are more following rectangular path and rectangular intersection. So how it's worked is, for example, we have our grid cell right there, and this one is a complicated one. So we have the main channel here that it's dendritic. And so I put dendritic here, and after that I have the proportion. So 1 means less than 10% of the grid cell, 2 means more than 20%. So it's more common. And here we have the parallel pattern. Those are less common. After that, we have the string bugs here on the peat plateaus, but also we have string bugs on the channel fen. Top physiography, we have collapse core right there, but also pond here and basins right there, and also ice wedge polygon. So if there is ice wedge polygon or not within the peat plateau, and those were right there that you can see with the image right now. And so we fill over, I think, 700 grid cell, and to have a good representation of the variability within the different ecoregion. But first, we want to understand how those dendritic peat plateau are degrading. So we went on the field and we use their ERT. Like I see, ERT is a really good tool to know how thick is the permafrost and if there's any process happening of degradation process. So we carry out, the first one was a 4-meter survey. So how the ERT works is more spacing you have, the deeper you're gonna go, but less precise you're gonna have it. So if we use less spacing, we're gonna go less deeper, but we're gonna have more definition for the, the for the first meter. And so we carry out the 4-meter because we thought that permafrost was way thicker than that, almost like 20 meter, here is 30 meter. But at this side, we find out that permafrost was super thin, around 5 or 7 meters. So the 4-meter survey was not very useful to characterize the degradation processes. So carry out the 2 meters just over the 4 meter. And this one, we were able to identify, confirm that permafrost was really thin, around 7, 9 meters. And this one here is showing the boundary, usually on clay and peat. It's in permafrost, it's around 200 ohms meters. So we know that boundary of permafrost is around this 2 green color. And this figure showed that lateral thaw is the main cause of wetland expansion and peatland degradation. So lateral thaw causes the widening of the fen and creating block erosion of peat surfaces and ground subsidence to the loss of area. So when I told you to remember about this ice rich dynamic deposit is the degradation is mostly happening within this ice rich dynamic deposit, and it's leading to the degradation of dendritic peat plateau by the widening fen. So we went to a different site, and this one we used the 4-meter, and this one it's at 1.5 kilometer from the one I just showed you, but the condition was very different, like no trees, super flat surfaces, very less foggy, and we carry out the 4-meter. And this one shows that there is 2 processes happening. We have connected talus, so lateral erosion from 2 sand between a peat plateau right there at 32 meters, but also we have stuff from below where we have fog. So it's telling us that the degradation of dendritic peat plateau is happening from lateral erosion, but also that from below that lead to the formation of bogs. And the age of those dendritic peat plateau are around 10,000 years old. That was super interesting because at first we thought that those landforms were very young, around 8,000 years old. And at the end, they are mostly 10,000 years old. And it leads to, I like this map. It's one of my result map, and it's giving me a lot of information. So at first we thought that they were young and inside the limit of glacial lake Mackenzie and McConnell, but the age showed that they were formed at the same time as the formation and the drainage of those glacial lakes. And so I calculate the annual normal temperature of each grid cell, the elevation that we are found just above the limit of glacial lake Mackenzie and McConnell. And the most important, it's the slope. So we have a very gentle slope. When we are on the field, we don't feel that there is any slope. But all dendritic peat plateau, most of them are four, where the slope is less than 0.5 degrees. So when we're in the field, we don't feel that super flat. But at the end, all the system will form with a very gentle terrain where there is a small slope. And so the distribution of dendritic peat plateau is around 22,000 kilometers square, so a bit less than grade per lake. So it's a very common landform. When we started studying it, we thought that there was maybe 3 or 5 like those kind of landform. But at the end, it's very common throughout the central Mackenzie Valley. And when I at first present this research with a postdoc, I got a really good question from Shala asking me if the drainage system were formed on the peat surfaces or the peat formed around the drainage. And it was a really good question that I need to think about when I was talking about I need to define the formation of the peat plateau. And I think at first we thought that those drainage was there first and the peat formed around it. And this map kind of indicate me that we were probably right because if we look at the orientation drainage, for example, number 4 is going to drain toward this a small s- outlet, not outlet stream here. Number 5 in the south is going to drain toward Fort Simpson. Number 2 drain toward the ancient lake. Here, this is the Nuriki Plateau just around the limit in the boundary of the ancient lake. So we know that because we have a slope, the water is flow somewhere. So probably those channel was there and the peat formed around it. And they are all pointing toward the ancient lake, except number 6 and this one were pointing toward Inuvik. And so first I look in the literature, just there was like if there was any lakes there. And I didn't find any information about an ancient lake. But when I was looking at my maps, I kind of figure out that the lowest point is the delta. So those systems are just draining toward Inuvik and Mackenzie Delta. And so after that, I got some result from my macro that straining that it's consistent with my hypothesis that those channel was formed first, and after that, peat migrated around it. Is that the first taxon, the first species or hydrophytic environment? So aquatic species that form mostly on stream and pools. So not even wetland species, both mostly aquatic species that were formed where there was streams. And after that, we have the wetland. So there was probably a stream and the peat formed migrated with inside the stream and formed the dendritic peat plateaus. And so this is the result from the branching patterns. We have 4 kind of branching, the multibasinal complex, dendritic, the classic one, the parallel, and the rectilinear. So in the south, the Bloomer plane represent the certain end member of our study area. So we are mostly multibasinal complex. So those are characterized by very large collapse core and basins and very large channel fan. And the dendritic one are characterized by very widespread channel, mostly form on very widespread organic deposit. We have the parallel when the O's are more linear and form where the peat are not very widespread, but very long. And the rectilinear, those are form where we have ice-rich polygon networks. So it's bringing you to the framework accentuate model that those are those patterns are not in they are not following an evolutionary path model. They are unique to their own setting and environment. So, for example, the rectilinear is going to more follow an ice wedge polygon network degradation path because they depend on ice wedge polygon growth and they are forming where we have those ice wedge networks and drainage basin. The parallel are mostly found where we have a higher slope and less organic deposits. So they are linear. The dendritic one or form where we have a lot of peat and usually higher elevation. And the multi-bacillary complex or form where permafrost is super warm, is super thin. So we're going to have mostly have more uh, degradation along the merging of the peat plateaus and internal and bog formation. So they are all unique and they depend to their own setting. Like rectilinear depend of ice wedge polygon formation. So cold permafrost, cold temperature, multi-basalt complex, it's linked to more warm permafrost. And it's probably that we probably never have been really a lot of ice wedge polygon even like 900 years ago, 100 years ago. So it's very unlikely that it start like a rectilinear pattern and that became multi-basalt complex because permafrost was never as cold or thick as it is in the north. So we need to think about the factor that influence the morphology and the evolution of those landforms. So that we look at the landscape morphology and the characteristics. So the first are the string bugs, or if they are on peat plateau or channel fen. And so we have channel fen mostly. We have string bugs on channel fen where we have the multibasinal complex and outlet collapse current basin, showing that they are highly degraded. And when we go to the killer plan that represent the middle of the central Mackenzie Valley, it's a good representation of every ecoregion in the middle. This one, we start seeing string bugs on ice wedge polygon and less string bugs on channel fen. And we start seeing that the formation of ice wedge polygon networks, but also we see a decrease of collapse current basin. So those endforms get less degraded when we go north. And when we look at the end member, the northern end member, we have the rectilinear pattern, and those are mostly related to ice wedge polygon and ponds. So they are unique and they are formed according to the local setting and environment and factor that influence the dynamic formation of peatland. So in this case, for this one, it would be ice wedge polygon network. So now it's my change detection paper. This one is to show you the change between the 40s and 2018. So the degradation is mostly happening in this site along the margin of the plateau and mostly where we have those big channelized bands. And so this is the result from mapping. So the first figure is just showing percentage of peat plateau and fan. It's not a surprise that the peat plateaus are degrading. So they're getting smaller and the number of fan are getting bigger. But what is interesting is in figure B, B is showing the area of bogs. So bogs are getting bigger and bigger. But if we go to C, the number of bugs are decreasing with time. So we have way less bug, but they get bigger. And it's probably due to the woodening of beds. So the formation of beds that just are just capturing the bugs with time. But between 2011 and 2018, I think I have 25 new bugs forming. So more bugs are still forming, but they just get captured the, by the fan. And the green rectangles show the annual loss rate. So the first part, the degradation was happening very slow. And after the 70s, we have a shift and an increase of air temperature and an increase of the annual loss rate with time. And if we look at Fort Goodall, we have the same process here. We have the peat are getting smaller, the fin are getting bigger. We have the same phenomenon here. So the bugs are getting bigger with time, but the number is getting smaller too. And here we have we have the same phenomenon. So the annual loss rate was kind of low. And after the 70s, it's get bigger. But we don't see a rise after 2008. It's more constant with time. And I think this result is mostly probably explained by the change type. So for Fort Goodall, we have mostly internal degradation. So it's mean formation of bugs and bugs expansion. It takes way more energy to degrade a peatland by internal and vertical tide than lateral tide. Because lateral tide is mostly along the channel where we have water flow flowing and way more heat and energy. So the Mackenzie Mountain side, it's 94% of just lateral tide degradation, which probably explain why we have a higher annual loss rate with that. And for the Fort Goodall, we have a lot of bugs. Probably there's less energy. And so this is why we have less degradation there. And so the dendritic peat plateau are really a common landform that go across the Northwest Territory, and they're forming by 2 meters of ice of 2 meters of peat and overlaying an ice rich dynamic deposit, hosting segregated ground ice. And the most interesting part was they are linked to the ancient glacial lake Mackenzie and McConnell that we didn't really expect that because we thought that they were probably inside the lake, but they were mostly found at the boundary and just above the lake. There's a lot of morphological variability, and this variability depends on factors like the ecoregion, the latitude, permafrost distribution and thickness. And because in the south, we're going to have mostly multibasinal complex pattern that link to thin permafrost and warm permafrost. In the north, we have rectilinear pattern. Those are linked to ice wedge polygon networks. And for example, the dendritic one, those are linked to higher elevation and more large till deposit, whereas the parallel or mosaic fine where the till the organic matter is not widespread, but we have a higher slope. So I'm working right now on a schematic showing the difference of dendritic pattern. And we have the rectilinear here with ice wedge polygon, the multibasinal complex with very thin permafrost, sporadic permafrost zone with fire, also fire history. And we have in the middle parallel in the dendritic pattern. So I'm still working on that. And when I mentioned that degradation of dendritic P plateau started 3070s, it's linked for after a rise of air temperature after 70. So figure A showed the air temperature, B show the mean and real air temperature difference. So we can see that after the 70, it's getting warmer with time. And I didn't find any significant difference for the total snow and total. So those dendritic pattern are mostly related, the degradation is mostly related to an increase of air temperature there after the 70s. And the figure on the right is showing the grid cell, it's showing the diagram degradation of the peatland within every grid cell. And this one, it's interesting because if you look at the first one, the audit there's no degradation. So pen are very stable and constrained within, like there's no water flowing, but with time, the outlet is getting wider and wider. So there's probably more water flowing out of those systems and connect to the Mackenzie Valley. And so it would be interesting maybe after to look at the mercury and methane that go outside of those systems and go into the Mackenzie River because now the outlet getting wider. So there's probably more water flowing outside those systems. And so to conclude this first section, so this is a very common landform across the central Mackenzie Valley formed at low elevation. And the main factor is the slope. So we need a very gentle slope to form the dendritic pattern. Therefore, until deposit, rolling plain, and hummocky terrain, those things segregate granite. So the degradation mechanism is more lateral toss, so a plateau edge in boundary between the plateau and the fan, but also internal toe that lead to the formation of bogs. And the dendritic peat plateau diversity is influenced by the location, discontinuous or continuous permafrost zone, thicknesses of permafrost, elevation, and temperature. So we need to start thinking about those factors that's going to influence the variability of the peatland morphology. Like I mentioned, the best example is the rectilinear pattern with the ice wedge polygon. So I'm working on cut and fill ice volumetric content estimation. This one would be a peer review application. And I'm working permafrost community mapping. Like I mentioned, I gained a relative experience with Michel when I was working for him. So I bring this experience at U of A, and Steve Coquelin actually really was very interesting to work with me on that for NWT community. So the first one is the cut and fill. This one, we just digitalized two types, but this one will be a first order estimation of the exercise. So how it works is we have an algorithm that fill, for example, a collapse core and bug, and it's fill the void and recreate the surfaces. But from our two first file digitized, we're probably underestimated the exercise because there is probably water at the bottom of the bog. So the model think that the water is at the bottom. So what we have to do is to use the CPT file that is more real to the real mean without the water. So in this, it's going to be, for example, we would have exercise between 0.3 meter and 1 meter of, uh, of exercise at some bog. So we want to extend the work. And what we're going to do next is go on the field and calibrate that with ERT and ground truth. And so we still need to work on that. It's still early on and I started this project during my intern at the TGS, and I'm going to work on that this summer. And now I start also working on community mapping. We went to Tulida, Central Valley. So it's following Michel our work at use Michel at classification. And the map on the left is showing permafrost condition, and on the right is showing the surface geology. And the next map we want to do it's the permafrost star string using our core. The two picture here or core from 2D that looks the diamond pellets. And it's real from the 50. This one on the right it's 50 centimeter to 80, and this one is 80 to like 120 centimeter. And we want to expand our work for Godot, but this project's going to probably be a master's student project, and I'm going to help with that. So just a small recap, there's a lot of variability of peatland morphology across the central Mackenzie Valley. It depends on factor that influence the pattern, like iceberg polygon or thin permafrost. And so the study is going to lead to a significant improvement in permafrost trajectory model. And the ice content is likely to be very variable across the central Mackenzie Valley. And I'm going to conclude that I'm hosting a session with Emma Street and Maria Quentin for the ERCUP 2025. If you're working on community, there's 3 sessions about community. So feel free to apply for my session. And thank you everybody to attend.
That was an impressive presentation and impressive work. Thank you so much for sharing it today.